Welcome, everyone. The core idea of this talk is that the brain doesn't operate on classical binary logic, the world of fixed truth values, but on a context-dependent logic where meaning emerges from relational structures. Polycontextual logic provides this missing framework. It treats emptiness as a structured potential, a space where meaning can emerge. This new approach lets us describe consciousness not as a computation over symbols, but as a dynamic orchestration of possibilities. For centuries, logic has been built on the idea of absolute truth. Something is either true or false. But quantum mechanics reveals a deeper reality, one where particles exist in multiple potential states, and outcomes depend on context. To model both quantum phenomena and the mind, we need a logic of potentiality rather than fixed values, one that can hold many possible truths simultaneously until a specific context selects ones. Polycontextual logic replaces the notion of value with the concept of the kenogram, an empty but structured position that awaits contextual filling. Morphograms extend this by forming networks of such positions. This shift from static truth values to dynamic relational places mirrors how quantum systems behave. They start not with certainty, but with structured possibilities that evolve toward meaning. In quantum physics, a system can exist in many states at once, a phenomenon called superposition. It's only when we measure that system that it chooses a particular outcome. This idea perfectly parallels polycontextual logic. An empty position can host multiple possibilities simultaneously until a context resolves them into a single outcome. Entanglement shows that quantum objects can be connected in such a way that a change in one instantly defines the state of the other, even across vast distances. This isn't communication. It's a shared relational structure. In polycontextual terms, this is called a transjunction, a link that binds separate contexts into a single indivisible whole. A qubit, the basic unit of quantum information, doesn't store a value. Instead, it represents a structured emptiness that holds multiple potential outcomes. Only when a measurement context is chosen does the qubit's potential collapse into a definite result. In this way, a qubit is conceptually identical to a kenogram. Superposition becomes even more interesting when seen through the lens of polycontextual logic. Each amplitude of a quantum state lives in its own contexture. Together, these amplitudes form a coordinated family of possible realities, a distributed potential across many logical spaces, all coexisting until a collapse occurs. Entanglement is more than just correlation. It's a logical connection that binds separate contextures into a single structure. The concept of transjunction captures this perfectly. Propositions in different contexts become inseparable parts of one relational reality. This binding underlies the computational power of quantum systems. Measurement is not merely observation. It's the selection of a context. Computation steers relational potentials through quantum gates, and measurement collapses them into a specific classical outcome. This collapse is always relative to the chosen basis, a contextual choice that determines which possibility becomes real. Quantum computation isn't about flipping bits, it's about evolving relational structures. Morphogrammatic processing captures this idea. Computation happens within structured emptiness, where patterns evolve and interact before any concrete values exist. This is computation as transformation, not as calculation. Quantum gates don't just manipulate values, they reshape potential structures. Gates like the Hadamard create superpositions, while C0 gates generate entanglement across contextures. Operations such as ROR and T represent relational transfers and couplings, turning computation into a morphogrammatic dance of structure. A quantum circuit is best understood as a relational evolution network. It guides the transformation of structured potentials through multiple stages until finally a measurement collapses them into classical results. Computation is the journey. The collapse is merely the destination. Remarkably, similar processes may occur in the brain. In models like ORCH-OR, tubulin proteins inside neurons can exist in superposed states, acting like biological qubits. These molecular circuits may steer relational information before it ever becomes conscious experience. Microtubules are not just structural scaffolding, they are networks of relational potential. Tubulin states influence each other non-locally, creating a pre-conscious field where information is processed before it reaches awareness. These networks may underlie the brain's ability to integrate vast amounts of information coherently. At higher levels, neurons and their assemblies form morphogrammatic structures of their own. Synaptic links function as transjunctions, linking different brain regions into unified cognitive wholes. These higher-order contextures are the stage on which consciousness emerges. A conscious moment is not a passive observation. It is the collapse of a brain-wide morphogram into a single, structured outcome. This collapse is shaped by relational context. It is the brain's way of selecting one coherent interpretation from a field of many possible ones. Before thoughts become conscious, they exist as evolving patterns of potentiality, proto-thoughts distributed across contextures. The brain is a generator of structured possibilities, continuously exploring configurations before awareness chooses one. Cognitive evolution follows a clear trajectory: superposition, transjunction, mediation, collapse. As potentials transform and interact, they approach a critical threshold. Collapse occurs when the system resolves into one coherent cognitive state, a thought ready for conscious experience. The brain doesn't just process information, it models itself. Through metamorphograms, it monitors, adjusts, and refines its own patterns of evolution. This self-referential capability is essential for learning, adaptation, and self-awareness. We now have a unified model linking logic, physics, and neuroscience. Consciousness emerges not from computation over symbols, but from structured collapse within a field of quantum relational morphograms. The brain is not a classical machine, it is a dynamic system of evolving potentials. This perspective radically redefines memory and learning. Instead of being stored as static data, memory is a dynamic relational field, constantly evolving and restructuring across contextures. Learning is the reconfiguration of these morphograms as the brain encounters new experiences. Building true artificial consciousness will require machines that mirror this relational structure. They must process structured emptiness, evolve quantum coherent relational patterns, and develop reflexivity, the ability to model and modify their own internal processes. Extending quantum logic into cognition is a two-way street. Physics gains new ways to model non-local structures, and logic expands beyond bivalence into multi-contextual reasoning. This cross-fertilization enriches both fields and moves us closer to a unified science of mind. We are already testing these ideas in simulations of brain-like morphogram evolution on quantum computers. The next step is experimental validation, comparing these simulations to real biological data and refining the models based on what we learn. The ultimate goal is to design machines that compute as the brain does, starting from structured emptiness, evolving relational patterns, and collapsing into meaningful results. Such machines could bridge the gap between artificial intelligence and artificial consciousness.